Okay, so we'll go back to our video. Today we are going to compare two different numbers. We have the number 3, or the square root of 2 plus the square root of 3 plus the square root of 4, so on and so forth, and nested the finite radical, all the way ending at the square root of 100. And of course the question is, which of these two numbers is bigger? So this can actually be done in two ways. The second way, I feel like it's going to be like a more of a try-hard method, if I want to put it like that explicitly. The first way, and we'll get to that eventually, the first way how we'll do this is more of an easier approach, such that if, of course, we don't really have to do anything with the number 3 that's on its own. Our main focus really is paying attention towards the finite nested radicals and how we can actually make that sort of comparison. So, of course, assuming we are not allowed such technical devices, calculators, anything, etc., because that would make things a little bit easier, such that you could obviously figure out which of the two numbers is bigger from there. Even though despite this is, finite nested radical all the way up to 100, which you'll be sitting there for a while just typing away on that calculator, but, you can do it that way, but here we won't be using such, advantage. So with that out of the way, and so why don't we actually just jump right in? So I'm actually just gonna put this in the brace such that we're actually gonna call our given finite radical over here, call that A. So now let's suppose that we define another number B, and it's gonna be in a similar fashion of just like the written for our given radical above. Instead, we have the square root of 2 plus the square root of 3, and instead of changing this from 4, we're actually, afterwards stopping from 3, we're actually gonna change this to now the square root of 100, and then plus the square root of 100, so on and so forth, so that it's actually a infinitely nested radical. So let me actually, fill in the gaps here first. Okay, so I have B is equal to this infinitely nested radical. Of course, with the two numbers from starting from 4 and then 100 and then going on so on and so forth, we can obviously see, we can make the comparison that indeed B is strictly greater than A. Okay, so with this in mind, let's now take our attention close to the infinitely nested radical, starting with the square root of 100 and so on and so forth. So let me call that number x. So x equals the square root of 100 plus the square root of 100, and then this continues on so on and so forth. So let me put this back over here. So assuming this is actually has some, convergence, so with that in mind, let's actually put this up so that it's actually infinitely nested, so the repeat cycles for, x equals a certain number, I can write that as x equals the square root of 100 and then plus x. Of course, we can actually solve this out to say I have x squared is equal to 100 plus x, and I can actually solve this on its own such that it's in the form of a quadratic formula, a quadratic polynomial, so x squared minus x, then minus 100, then set that equal to 0. So of course we want to solve for x, so by applying the quadratic formula, so x is equal to, so I have negative 1, so that means 1 plus minus the square root of 1 squared minus 4 times 1, and then times negative 100, then that being divided by 2 times 1, so 2. And I can simplify this out, so I have 1 plus or minus the square root of 401 divided by 2. Now, of course, with this being the square root, it's a positive function, so we can actually just disregard the negative. So that means I have, therefore, x is just simply going to equal to 1 plus the square root of 401 and then divided by 2. Okay, with that in mind, let me actually just box this for our x. And of course, we can actually make a little bit of a comparison focusing on the square root of 401. So if we know that the square root of 400 is equal to 20, and we have a square root of 401, we can make that comparison and say that 20 is strictly less than the square root of 401, which of course can be strictly less than 21. So with that in mind, so we just create this little bound for x. So I have that x is strictly less than 1, then plus 21 from that bound over here that we created, then divided by 2, which indeed that's simply just going to equal 11. Okay, so with this in mind, I have that now b, which was the number that we're starting with over here, and so we can actually now utilize that bound that we just created for, the less than 21, then plug that back here to get that x less than 11 back to substitute it over here for b. So putting that into comparison, I have that b is strictly less than the square root of 2, then plus the square root of 3, and then add this with 11, okay? So that means that will yield us with the square root of 2 plus the square root of 14, So now let's pay attention to our square root of 14. So we know that indeed that the square root of 9, which is going to equal 3, is strictly less than the square root of 14, which is strictly less than the square root of 16, aka 4. So that means 3 less than the square root of 14, which is strictly less than 4. So if I actually just put this back over here for the substitution of our bounds, so now we have that the comparison b is strictly less than the square root of 2 plus the square root of 14. So just from before over here, then I could say that this is strictly less than the square root of 2 plus 4, which is indeed the square root of 6. And of course, we know that that's strictly less than the square root of 9, so that means aka 3. So less than 3, which we actually have the comparison that 3 is going to be a lot bigger than what we said b is, which is over here, which we said that a is less than b from our given. So therefore, a, which is our given finite nested radical over here, is strictly less than b. A strictly less than b, and then strictly less than 3. So therefore, 3 is going to be the bigger number out of these two. So that's one way done. So now let's actually get into the second method, the try-hard method. Okay, now let's move on to the second method. So what we're going to do is we're actually going to, suppose a function, or not a function, but a numbers, of the infinitely nested radical. I suppose we'll let x, the variable, equals square root of 2 plus square root of 3 plus the square root of 4, so on and so forth, so infinitely nested. So of course I have something of a finitely nested radical, but the process what we were doing is still valid. So with that in mind, now let's suppose I actually square both sides of our equation. So I have x squared, so that means I'll just get rid of that radical over here. So 2, and then plus the square root of 3 plus the square root of 4, and then, well, plus the square root of 5, then so on and so forth, continuing over here. Interestingly, so if I were to do something a little bit different, so I now have x squared, then subtract the 2, which is indeed just equal to the same thing over here. So 3 plus square root of 4 plus square root of 5, then so on and so forth. Okay, so here's what we're going to do. Let us go back to the original equation for x equals this infinitely nested right here. What we're going to do is let's actually multiply numbers from both sides. Let's specifically multiply the square root of 3 divided by 2. So that side, and then now set this equal to, so the square root of 3 over 2, then multiply by this infinitely nested radical over here, so 2 plus square root of 3 plus square root of 4, then continuing on, so on, so forth. So here's the interesting thing that we're actually going to do here. So let us actually move that square root of 3 over 2. We're going to put that back inside of our radical. So what that entails is that if I put that back in, that means I'm multiplying 3 over 2 back into inside. I'm also going to multiply the 3 over 2 back into the inside of here as well. So that entails that what we'll have is, so continuing forward, is that we're going to have, so the square root of 3, then plus 3 divided by 2 multiplied by the inside of over here. So that means I have the square root of 4, then plus the square root of 5, so on and so forth. And so that will mean that moving the 3 over 2 back inside, I had to square the 3 over 2 quantity back into here, then do the same thing with multiplying that quantity. So let's see, that'd be 9 over 4, then times 4. So that means I have a 9 from this after doing that multiplication of 3 squared divided by 2 squared times 4. So let's see, I have 3, then plus the square root of 9, and then multiply that. So that number squared is going to be 9 over 4 multiplied by the square root of 5, then so on and so forth. Okay, then let me continue on with one more line. So of course, just repeat the same iteration. So I have 3, then plus the square root of 9, then put that back inside, square that number, and then multiply that by 5 and multiply that quantity to the continuation. So what that will yield us, I have is plus, and then the square root of 405 divided by 16. Then add this with 81 divided by 6, that's times the square root of 6, and then continue on, so so forth. So we're just going to stop there for now. It's infinitely nested with this continuation over here with the following with the ellipse. You'll notice that this specific number over here with the subsequent radicals continuing on, so forth, after multiplying the quantity of the square root of 3 over 2, this is actually going to be larger compared to how we have x squared minus 2 is equal to this infinitely nested quantity over here. So with that in mind, I can actually make the comparison and say that x squared minus 2 is strictly less than the square root of 3. I'm supposed to write that a bigger radical symbol. The square root of 3, then divided by 2, and then multiply by x. Okay, so again, by doing the same process a little bit, we get that in just a quadratic formula by itself, or the quadratic polynomial. With the inequality side, I have x squared, then minus the square root of 3 divided by 2 times x, and then minus 2, which is strictly less than 0. Okay, then that would mean that I can actually just apply the quadratic formula to solve for x. This one's a little bit more tedious work. I'll skip that step. That what we'll do is now we have that x is strictly less than, so we have the square root of 3 divided by 8, and then add this with the square root of 19 divided by 8 from the quadratic formula over there. So we're actually going to be using a little interesting fact that, and you can actually look this up. I'm sure there's more into detail about when it comes to the generalized mean, or even there's more information about it on the Math Stack Exchange, that we're actually going to use the fact that the sum of two squares is actually less than twice the square root of the average of those, the two sums of the radicals. So what this means is that I have that x, so strictly less than, so this is going to be the same thing over here, so 3 divided by 8, and plus 19 divided by 8. We're going to be utilizing this bound such that I have now 2, then multiply the 11, or the square root of 11 divided by 8. Then we're going to continue then using with the extreme left and extreme right hand side over here. I'll square both numbers on both sides. So x squared is strictly less than, so if I squared this number, I have 4, then 4 times 11 divided by 8, that'll simply just reduce down to just 11 divided by 2. And we can actually make the quick observation and say that that is indeed strictly less than 9. So finishing off, just square both sides. So I have that x is strictly less than 3. So using that comparison, that x that we actually call this infinitely nested radical over here, doing the same thing from, it's similar, of course this is finite, but this is infinitely nested, so with infinitely nested is going to be a larger number than that. That actually comes to the conclusion that whatever this is, like the infinitely nested number that number comes down to / converges to, we can obviously say that 3 indeed is going to be the bigger number out of these two. So with that, that completes our two methods. Hope you learned something interesting with a different perspective in mind when, doing comparison with two numbers. And yeah, that's pretty cool if you ask me.